Good afternoon, everyone, and welcome to the third in our series of expert webinars exploring the issue of nuclear power in New York. Thank you for joining us. We are here today at a critical moment, and right here in New York, major decisions are being made that will shape our energy system, our environment, and our public health for generations. These decisions are being framed as pragmatic, necessary, even inevitable. But are they? At the federal level, President Trump has been cutting support for renewable energy while he promotes expanded fossil fuel development. Energy companies continue to invest billions in new natural gas pipelines, locking us into decades of additional greenhouse gas emissions. And here in New York, Governor Kathy Hochul has announced plans to pursue new nuclear facilities, citing what is described as a growing electricity demand, a demand that many experts argue is overstated or could be met more safely and affordably through increased efficiency and the rapid deployment of renewables. Nuclear power is one of the most expensive forms of electricity ever invented. New nuclear projects routinely run billions of dollars over budget and take far longer to construct than wind, solar, or energy storage systems, often a decade or more. At a time when we urgently need rapid climate action, can we afford to wait that long? And then there are the risks. From uranium mining and radioactive waste to the long-term contamination and residential proximity exposure, nuclear power carries environmental and human health consequences that can be devastating. The legacy of accidents at places like Chernobyl and Fukushima remind us that while catastrophic failures may be rare, their impacts are profound and long-lasting. Here in New York, we have our own history, from decades of debate over plants like Indian Point to ongoing concerns about waste storage and decommissioning. These are not abstract policy questions. They affect real communities, real ecosystems, and real people. This webinar is an opportunity to step back from political talking points and examine the evidence. How realistic are plans for small modular reactors in terms of cost or construction time or safety? Have any of these new ideas solved the long-term risks that have always plagued nuclear power, like what to do with nuclear waste? Shouldn't we really be talking about better, faster, safer alternatives available to New York that can help us meet our future energy needs without jeopardizing our health, our safety, or our children's future? To help answer these questions, it is my pleasure to introduce our featured speaker for today, Dr. Gordon Edwards, one of North America's leading experts on nuclear power and radioactive waste. For decades, Dr. Edwards has worked to educate the public about the scientific, environmental, and ethical dimensions of nuclear energy. He brings a deep understanding of both the technical realities and the broader societal implications of nuclear policy. You can read more about his background on our website. Please join me in welcoming Dr. Gordon Edwards.
Thank you very much, Doug, and thanks to everybody for showing up for this webinar. So I did not choose this title, which is Debunking Nuclear Hopium, but it reminded me of when I was in high school, when nuclear power was presented to me as a high school student as clean, safe, inexhaustible, and affordable. And I thought, wow, it sounds great. And I was very much in favor of it. Unfortunately, I found out that these adjectives none of them are actually accurate. So hopium is a kind of a combination of blind faith based on partial information and addiction, which needs somebody to push you in that direction. And this is from a comic book that was distributed when I was young with the Canadian Nuclear Society. So I'm going to start part one of my talk by talking about small modular nuclear reactors and where the idea for small modular reactors, I believe, originated. SMR could also be called spending money recklessly, which I believe is a true statement, because these small modular reactors are going to be very, very expensive. The problem is that in 2019, it was already crystal clear that the nuclear industry had been stagnant for over 25 years. This graph from the World Nuclear Association shows very clearly what happened, a kind of an exponential growth at the beginning, and then an absolutely flattening out for 25 years, for a quarter of a century. In fact, in 1996, there were 438 reactors in operation in the world. By 2019, there were 442, only four more reactors. And meanwhile, the share of nuclear as a share of global electricity use had declined from 17% to 10%, and now it's gone down to 9%. It's still going down, and nobody expects it to reverse itself anytime soon. In fact, in 2019, the American Society of Mechanical Engineers made the following statement. The International Atomic Energy Agency, looking ahead to 2050, sees the most optimistic global electricity market share for nuclear as only about 5%, down from 10% today. And in the United States and Europe, it steadily declines to between 3 and 5% of the market, constituting a potential for market failure. In other words, nuclear can just price itself out of the market altogether. Now, the first nuclear renaissance was around 2001, and it was in response to this state of affairs, this sad state of affairs for the nuclear industry. They knew they had to do something to revitalize the industry and to get it going again. And so they declared that there was going to be a nuclear renaissance. There were going to be hundreds of new reactors built around the world. But in fact, only a few were ordered, and there was a kind of a litany of failures in connection with those attempts. The bankruptcy of Westinghouse occurred in 2017. They had $9 billion in losses from new nuclear projects, mainly the four AP1000 reactors in Georgia and in South Carolina. Now, these reactors were the first reactors to be ordered in 30 years, and licensed, I should say, for construction in a 30-year period. There had been a 30-year drought up to then. And the U.S. federal government had given $8.3 billion in loan guarantees on the financing of the four reactors. As we know, South Carolina abandoned the project, Georgia did not, and the Georgia reactors are now up and running, the Vogtle reactors, and they are considered to be the most expensive per megawatt installed capacity ever in the world. Now, the collapse of the French giant Areva happened also around the same time with regard to the Finnish reactor, the Olkiluoto 3 reactor, 1,400 megawatts. It was supposed to be operational in 3 years after being ordered in 2005, and it was going to cost 3 billion euros. It actually started up in March 2022. That's 19 years later, and cost 11 billion euros. That's $12 billion approximately. Took 6 times longer to build than promised and cost 4 times more. This is one of the stars of the nuclear renaissance, and it bankrupted Areva. The company had to be absorbed by Electricité de France. So let me say a few words about nuclear fission and why this is endemic to, no matter whether you have a large plant or a small plant, no matter what the technology is, no matter what the fuel is, no matter what the coolant is, doesn't matter about the design. There are certain things about nuclear fission which are fundamental. Henri Becquerel in 1896 discovered radioactivity. He discovered that lumps of uranium ore or thorium ore taken from the ground are radioactive. They give off a kind of an invisible ray which will expose photographic plates even if they're wrapped in thick black paper. He didn't understand where this energy came from. You can't see radioactivity, but if you put one of these rocks in a cloud chamber, you can see the tracks that are condensation tracks of the radioactive emissions that are given off from uranium ore or from thorium ore. Now, the amazing thing about this energy that's pouring off of this rock is that it has been going on for millions and millions and millions of years without stopping, 24/7, day and night, constantly pouring out. Now, it wasn't too difficult for the scientists to do a calculation to figure out how much energy that was if you added it up over a few thousand years. And it was clear that it would be enough to cause major damage to the Earth. And in fact, it did later on. The city of Hiroshima was destroyed by one uranium bomb on August 6, 1945. But way back in Becquerel's day, they didn't believe this was possible because radioactivity cannot be speeded up or slowed down. It cannot be stopped. It cannot be turned off. That's why we have a radioactive waste problem. These radioactive materials are dangerous to living cells. They cause cancer and other diseases. And so we have to keep them out of the environment of living things if we want to have a safe environment. Now, it was also discovered that we could harness this energy. We could build a nuclear reactor and keep the chain reaction of uranium going so as to harness the energy, boil a lot of water. That's basically what it is. It's a way of boiling water and use that steam just as we do in a coal burning plant or an oil burning plant to turn the blades of a turbine and generate electricity. The difference is how you boil the water. Now, the uranium turns out to be the key element in all nuclear fission technology. Without uranium, there would be no nuclear weapons of any description and no nuclear reactors of any description. So uranium is the key. And nuclear fission was discovered a lot later, only in around Christmas time of 1938. During the Christmas holidays, between 1938 and 39, when a neutron strikes a fissile uranium atom, that's a rare kind of uranium called uranium-235. It's only 7 atoms out of 1,000. When you mine uranium out of the ground, 7 atoms out of 1,000 are this type of uranium. But that's the kind that is needed for a nuclear chain reaction, because when a neutron strikes one of these atoms, the atom splits into 2 smaller atoms, which are highly unstable and therefore intensely radioactive. And the result is energy is released and these fission products are created, which are the bulk of the radioactive waste from nuclear reactors, and more neutrons are given off. Now, those more neutrons are important because they trigger more fissions and go on and maintain a nuclear chain reaction, whether that's uncontrolled, as in the case of an atomic bomb, or whether it's carefully controlled, as in the case of a nuclear reactor. And some of those neutrons also go on to produce more radioactive byproducts in addition to the fission products. So what do the extra neutrons do? Well, as I said, they keep producing fission products. Every time an atom splits, you have 2 radioactive byproducts, fission products. But they also turn some of the uranium into plutonium. In fact, the uranium that doesn't split becomes heavier and becomes a transuranic element, which we don't find in nature, called plutonium and americium and neptunium and another number of other names. In addition, these extra neutrons collide with non-radioactive elements that are just sitting there in the concrete and the steel of the reactor itself and turn those atoms into radioactive atoms. These are called activated atoms. So radioactive atoms are created right in the makeup of the steel and the concrete. And that's why the decommissioning of a nuclear reactor is very difficult. But one of the most significant things is that when a neutron hits a uranium-238 atom, uranium-238 is the most abundant type. It's over 99% of all the uranium we mine from the ground. When hit by a neutron, it turns into a heavier than uranium atom called plutonium. And that turns out to be a powerful nuclear explosive. In fact, it's the backbone of all the nuclear arsenals in the world today. So those extra neutrons are very important for people who have nuclear weapons programs. That's where they get their plutonium from. In fact, the very first reactors that were ever built were built for the sole purpose of producing plutonium for bombs. Later, it was realized very quickly that plutonium could also be used as another nuclear fuel besides uranium-235. Now, this glass paperweight is the exact size of the plutonium ball used in the Nagasaki bomb. That's how much plutonium you need to destroy a city. It's about 3.2 kilograms. And incredible how much energy is packed into the nucleus of those atoms. The amazing thing is that one of the smallest things that you can possibly imagine, the nucleus of an atom, extremely tiny, contains the most powerful force in the universe, which is the nuclear force. And it's liberating that nuclear force that is the secret of nuclear energy. Now, here's a picture of Howard Moreland, who was a journalist who wrote an article about making an H-bomb, a hydrogen bomb. And you'll see that even in the most sophisticated nuclear weapons, there is still a ball of plutonium necessary. This is a fusion thermal nuclear weapon that uses fusion, but that ball of plutonium at the top is needed to get the temperature up to 100 million degrees, which is necessary to get the fusion started. So what are the activation products? I mentioned about activation. When a stray neutron is absorbed by a non-radioactive atom, the result is often a radioactive atom. It's called an activation product. For example, here in Canada, we use a heavy type of hydrogen called deuterium. It's not radioactive. But when it absorbs a neutron, it turns into an atom of tritium, which is radioactive. These are isotopes. They're called isotopes, varieties of hydrogen. Hydrogen being the most abundant atom in the entire universe, the most abundant substance in the entire universe, and fundamental to all living things. Tritium is the radioactive form of hydrogen, and a great deal of it is made in nuclear reactors and in nuclear explosions. Some of it also comes from nature in the form of cosmic radiation from outer space. So there is a background level of tritium, but what is produced here is man-made. Water is activated and produces radioactive tritium. Air is activated, produces radioactive carbon-14, and all organic molecules have carbon and tritium in them. So these radioactive varieties become incorporated into our DNA. When I say carbon and tritium, I should have said carbon and hydrogen. All of our organic molecules have carbon and hydrogen. Those carbon atoms and those hydrogen atoms can be easily replaced by the radioactive varieties. So we can have these radioactivity right into our own organic molecules. Even the structural materials in the core area of the reactor become radioactive waste, dangerous for thousands of years. Steel, concrete, zirconium. So they cannot be recycled, but must be stored forever as radioactive waste. Here's a list of selected radionuclides in irradiated nuclear fuel. This list has about 211 different elements listed, varieties of elements, all of them radioactive, almost all of them man-made, human-made. Well, in fact, in this case, in the case of nuclear fuel, the only ones that are not human-made are the uranium and thorium atoms, which are there to begin with. This list of 211 man-made radionuclides contained in irradiated fuel is by no means complete, according to Atomic Energy of Canada Limited. And by the way, the radioactivity is so intense that if you wanted to dissolve it, just 1 year's radioactive waste from one nuclear reactor, just 1 year's worth of radioactive waste, you'd need an amount of water about the volume of Lake Superior to dissolve that amount of spent fuel, it's called irradiated nuclear fuel, to the maximum levels of contamination for drinking water allowed by law. So that's why this is a very serious problem. And even after 1 million years and even after 10 million years, the amount of water needed is still very considerable. The U.S. Geological Survey pointed out that even after 1 million years, you'd still need about all the water in the Great Lakes to dissolve the waste from American reactors to the maximum level of contamination allowed. So the second nuclear renaissance began around 2018, and this is the small modular reactors. The idea that the nuclear industry had is that the first attempt to revitalize the industry was not a success. It was a fiasco. So let's try again. Maybe the big reactors are too expensive. Maybe we should try small ones. Maybe that'll work better. But the small modular reactors are really a kind of a logo. It's a slogan that doesn't have a precise definition. It's really a grab bag to cover hundreds of different designs. In fact, there's over 120 different designs on the market right now that people can develop ready to go. So the rationale for small modular nuclear reactors was partly because large reactors are too expensive to finance for many jurisdictions, and they're also too powerful for small grids in some countries. SMRs are smaller, they can be modular for mass production. By making them smaller, you also make them more expensive. But maybe if we mass produce them, we can lower the cost down to where it's affordable again. SMRs can also deliver heat as well as electricity. They can be a little more flexible. You can also store that heat for flexible usage. Of course, you could do that with large reactors too, but they wanted to think of different ways of marketing small modular reactors. And one of the lines they use is that small modular reactors can serve as backups for renewables because renewables are intermittent or variable. However, that has not been the case up to date. In fact, nuclear power tends to crowd out renewables rather than vice versa. The problems for small modular nuclear reactors is they're very costly. Mass production is needed to try and keep the cost completely from going completely out of line. Also, you have more concentrated fission products and activation products. When you make the reactor smaller, that means the structural materials are much closer to the core of the reactor. And so activation becomes a bigger problem than it was in the larger reactors. The materials that are close to the core get very radioactive. There's also a less massive containment. And so how do we protect it? Well, let's try and put them a little bit at least underground so that they're not completely vulnerable to things like airplane crashes and malicious acts. The big problem, however, is there's too much competition. There's no single design that can dominate the market to such an extent that they can make it cheap and justify mass producing them. Public money is needed because private funding is very hard to find. Lack of markets and slow deployment, these are big problems. Now here's an example, the NuScale power modular reactor, the NuScale power module. It's licensed for construction in the USA, but when projected power costs rose sharply, the clients down in Utah, the UAMPS people, they backed out of it. And so that project was canceled in 2023. It looked like it was going somewhere, but it got canceled. This is a 77 megawatt light water reactor, a PWR, pressurized water reactor with steam generators, boilers, and passive safety features. Passive safety features are features that don't depend upon electricity supply, so that you don't need to have pumps running in order to keep the core from melting by removing the so-called decay heat. Here's another called a micromodular reactor by the Ultrasafe Nuclear Corporation. It's a gas-cooled 5 megawatt reactor with a molten salt heat storage system. It was supposed to be built in Canada, just north of the nation's capital, on the Ottawa River, at what's called the Chalk River site in Ontario. But Ultrasafe Corporation filed for bankruptcy in 2024, and so this project is paused indefinitely. The BWRX-300 is a boiling water reactor that doesn't require steam generators. The water is allowed to boil right in the core of the reactor, and then the steam is used to generate electricity. It's a 300 megawatt plant. It's estimated to cost 6.5 billion Canadian dollars to build. That's equal to the cost per megawatt of the Vogtle plants, which, as I mentioned earlier, were regarded as the most expensive electricity capacity ever built. So we're not talking about cheap. We're talking about very expensive power. It's under construction because they've got a construction license from the Canadian regulator for the first of 4 units to be built east of Toronto at Darlington on Lake Ontario. Now, if you take a closer look at the design, you'll see that it's bigger than you think it is. It's actually 21 stories high, 10 stories above ground, and another 11 stories below ground. So calling this a small modular reactor is a bit of a stretch. It doesn't seem very small. Also, it's not so modular either. It's the first of a kind, and so it's going to be put together by hand. And a workforce of up to 4,000 has been cited by the Prime Minister, who has invested federal money in it as well. So this is really not small and it's not modular, but it is nuclear. And the funny thing is, that's the one thing they leave out of their acronym. They call them SMRs, not SMNRs. They leave out the N. The S, small, is debatable. The M, modular, is also debatable. The nuclear is not debatable, but it's not there. And maybe that's because they don't want to call attention to the fact that nuclear is where all the problems really lie. Now, the BWRX 300 is a 300 megawatt, as I mentioned. It's based upon an earlier version, which was licensed to be built, but never built, in fact, in 2011. That's the same year that the Fukushima reactors melted down. They were also boiling water reactors in the same evolutionary line as these other ones. And so what they did was they took the ESBWRs, called the economic boiling water reactor, and they removed a great deal of the safety systems in order to shrink it down. And so they got a smaller reactor, the BWRX 300, but the price they paid is to eliminate a good many safety systems, including the emergency core cooling system, the core catcher, which was in case of a meltdown, it would spread the core and prevent it from melting through the bottom of the reactor. They got rid of that. They got rid of the pressure relief valves in the core of the reactor. It means that if the pressure builds up, they can't relieve it by opening a valve. They're going to relieve it a different way using what's called a condenser relief system. So this is a passive system. It's not a complete design. Everybody has acknowledged that it's still not a complete design, but they're building it anyway. So the nuclear fission by itself raises several problems. The first problem is the nuclear waste. That's going to be a problem for many thousands or even millions of years. Problem number two is the possibility of a nuclear catastrophe. Now, nuclear catastrophes cannot be completely avoided because what a nuclear catastrophe is simply releasing the radioactive materials that already exist inside the reactor. When the uranium atoms are split, you have all those fission products building up, and they're there. There's nothing you can do about it. You can't wish them out of existence. Anything that releases that material into the environment is going to be catastrophic for the neighboring environment. And so that's what nuclear catastrophes are. This could happen by, for example, dropping a bomb on it. And it's been pointed out by nuclear physicists in Britain that if you had developed nuclear power before World War II, then large parts of Europe would be uninhabitable today because of World War II, because those plants would have undoubtedly been targeted. And you would have massive releases with powerful bombs. And of course, sabotage as well. Then we have problem number three, nuclear decommissioning. That's what to do with all the structural materials which have become radioactive waste. You can't recycle them. For this reason, nuclear power is sometimes described as the ultimate throwaway society, the ultimate in throwaway society, because you can't reuse that material. Problem number four is very serious, and that's spreading nuclear weapons unintentionally to other countries by giving them the wherewithal, namely the plutonium, that they don't otherwise have access to.
I want to give you a chance to catch your breath because you've been giving us unbelievably interesting information. I didn't want to stop you, but I did want to give you a rest. We've had a question from the audience, and I'll just read it. Nuclear advocates like the DOE are claiming that fast reprocessing can eliminate waste by 95% and leave only waste that has a need for waste disposal for 300 years. I presume 10 half-lives of strontium and cesium. I guess they presume multi-passes of reprocessing. Is this possible? Probable? I'm just trying to counter the claim that you could reprocess over and over again to eliminate and reduce waste.
Yeah. Okay. When we talk about reducing waste, this is called reprocessing the spent fuel. And you can't do anything with the fission products. The fission products are the bulk of the radioactivity. It's the heat from the fission products that causes reactors to melt down. And those are not recycled. Those are not reused. They cannot be reused as fuel. The only things that can be reused as fuel are the plutonium. The plutonium, which is only one of 211 materials. Well, it's 6 because there are 6 isotopes. And there are other heavier than uranium atoms which can also be recycled, but that's a small fraction of the actual waste material. When they talk about reducing the waste, they're talking about shrinking the volume, but the volume was never the problem. In fact, the industry always likes to boast at what a small volume of waste it is. Reducing the volume simply concentrates all the radioactive poisons in a smaller volume. And in fact, it's far, far more radioactive than the spent fuel in per kilogram. So it's more concentrating the waste than eliminating them. The only waste that you eliminate are the plutonium isotopes, but those are fissioned, and that produces more fission products. So every time you go around that cycle that you were referring to, reprocessing over and over again, you're multiplying, 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 multiplying the fission products. It's building up more and more and more. And that is the bulk of the waste for the first 1,000 or so years. That's the main source of the radiotoxicity and the heat generation from the waste. Meanwhile, the plutonium, the danger with reprocessing is that you make that plutonium accessible not only as fuel for reactors, but also as material for bombs. Mm. And so you are doing the would-be bomb makers a favor by getting rid of the fission products so that they can get their hands on the plutonium and use it directly to make bombs. It makes it a lot easier for criminals or terrorist organizations or rogue states to make atomic weapons. If there is plutonium reprocessing going on, it saves them a lot of trouble.
Oh, man. We've got another question. How does the Navy manage its nuclear waste in all the nuclear vessels that they have?
First of all, the Navy uses 93% enriched uranium, which would never be allowed in a civilian reactor. This is weapons-grade uranium. It's the same uranium that was used in the Hiroshima bomb. And anybody who had access to 93% enriched uranium, even a terrorist organization, could make a relatively simple atomic bomb with the power of the Hiroshima bomb. It's called a gun-type bomb, and it's not very difficult. So that's one point. Secondly, the waste is simply brought back to Idaho and joins the waste stream that we have. So it becomes extremely, that waste, because of the fact that the uranium is so highly enriched, enriched means that, remember I told you that there's only 7 atoms out of 1,000 that are uranium-235? Well, in that reactor fuel in a nuclear submarine, it's 93 atoms out of 1,000. 93 atoms out of 100, I'm sorry, that are uranium-235. That means that all the fission products are that much more intense. So that spent fuel is way more radioactive per kilogram than any spent fuel we get from a commercial reactor. And it is a problem. It is a problem. We have not safely disposed of that stuff any more than we safely disposed of any of the rest.
Mm. Okay, I'm going to let you get back to part 2 of your presentation, and then we'll have some more questions after that.
Part 2 is advanced nuclear reactors and fusion. So what are advanced nuclear reactors? Advanced nuclear reactors are not really well defined either. It's more of a slogan again. But in the United States of America, according to the U.S. Nuclear Regulatory Commission, it means unconventional cooling. And instead of using water as a coolant, we can use other coolants. And for example, you could use gas as a coolant. Carbon dioxide gas can be used as a coolant. That was done in Britain. They built way back right after World War II, they built a whole fleet of gas-cooled reactors. And gas-cooled reactors in other countries too, in Switzerland, for example. There was one gas-cooled reactor that blew itself to kingdom come, because if the gas leaks out, you have a loss of coolant just like you do in a normal reactor if you lose the water. But it's not gas that they're primarily thinking about. When they say advanced reactors, they're thinking about things like liquid metal. Liquid metal is very, very hot. And in particular, they think about liquid sodium metal. Liquid sodium metal can act as a very good coolant. It's very good at exchanging the heat and taking it to the boiler where water is boiled to produce steam for the blah, blah, blah. But the trouble with sodium is that on contact with water, it's explosive. If you drop a little piece of sodium into a glass of water, it burns spontaneously on contact with water with an intense heat. And at that temperature that the coolant is in a sodium-cooled reactor, it'll also burn in oxygen immediately. So we have a real problem there. I just wanted to say that one of the big problems with that the nuclear industry has with marketing its small modular reactors is that solar and wind are so much cheaper, even with storage. And the thing is that every year, solar and wind get cheaper and cheaper, and nuclear gets more and more expensive. And also, the storage is getting cheaper and cheaper. So it's a double whammy. The poor nuclear guys are facing stiff competition. And in fact, the solar and wind are growing at an exponential rate worldwide, far, far faster than anything that's happening in the nuclear domain. Um, and here's an example in Texas, a case study in Texas. They had a record battery discharge, an immediate battery discharge of 10 gigawatts. That's equivalent to the output of 10 nuclear power plants. 10. A gigawatt is 1,000 megawatts. So imagine getting that much energy out of batteries in very quickly, instant battery discharge. And also, it covered a load of 18% of the load of Texas in that at that particular time. So these batteries are getting very, very good, and they're getting very, very fast, and they're getting cheaper and cheaper. That's a problem for the nuclear industry. This is from the U.S. Energy Information Administration of several years ago, but it just shows even then how that green line that's shooting up is renewables, and the line at the bottom is nuclear. It's just not being able to get off the ground compared with renewables. And that's true worldwide. The COP28 in 2023, you remember, the previous COP, they made a pledge worldwide of over 200 nations to triple renewable energy and double energy efficiency by 2030. Whereas the nuclear guys got together and 25 of them made a pledge among themselves, not an official pledge, to triple nuclear power by 2050. Notice that's 20 years later. It's 20 years later, and it's much less achievable than the tripling by 2030 of renewable energy. Here's a showing. The renewables are at the top there, the yellow and the orange, and the fossil fuels and geothermal, ocean hydro, and so on. And the purple is the nuclear. And you can see that it seems feasible to be able to triple renewables the way it's growing right now. If you extrapolate that, it seems plausible to triple it by 2030. Whether we'll achieve that or not, we'll have to wait and see. But you can be darn sure that nuclear is never going to make it by 2030, probably not by 2050 either. Meanwhile, people often say, well, if you phase out of nuclear, or if you devalue nuclear, then you're going to have rising greenhouse gases. You're going to have more climate change. Germany shut down all of its 17 nuclear reactors, all of them, on time, on schedule, and they have been reducing their greenhouse gas emissions while they have phased out nuclear power. And of course, part of the reason for that is because they phased in a good deal of energy efficiency, which is the cheapest way to offset greenhouse gas emissions, and renewables, which are the next cheapest way. So they're doing okay. Now, let's talk about advanced reactors. Molten salt coolant, first of all. I believe that they've talked about using molten salt coolant possibly in New York. The original molten salt coolant reactor was designed for airplane engines. They wanted to make airplane engines nuclear powered. And this is way back in the 50s. And here are two abandoned airplane engines that are nuclear and that are molten salt reactors. Those are the original molten salt reactors. It was canceled in 1961 by President Kennedy, who saw that it was an enormous waste of money. And there was no sign of it reaching completion or of reaching an end to the escalating cost. So he just terminated it. Now, Alvin Weinberg, who was at the Oak Ridge Nuclear Laboratories, he took over the project. He was in charge of the project to begin with. He moved the whole operation to Oak Ridge and built a molten salt reactor experiment at Oak Ridge. And this ran for a period of about 5 years in the 1960s. And it used plutonium as fuel, it used weapons-grade uranium as fuel, and eventually it used something called uranium-233, which doesn't occur in nature. I'll talk about that later. And now we have, in 2017, there was a news article saying the contaminated molten salt reactor experiment may have to be entombed in concrete because they don't know what to do with this. All of the molten salt is thoroughly contaminated with radioactivity. It's full of fission products. It's highly radioactive. It's highly corrosive, and they really don't know what to do with it. They still have not dealt with that problem. It's an ongoing problem. So another advanced concept is liquid sodium metal coolant. Now, the first one was the experimental breeder reactor down in Idaho, and the Argonne National Laboratory ran this as an experimental breeder reactor. A breeder reactor is a reactor that makes more fuel than it uses. Now, how is that possible? Well, they're talking about plutonium. That if you surround a plutonium-fueled reactor, if you surround it with a blanket of uranium-238, then the stray neutrons turn the uranium-238 into plutonium. And if you play your cards right, you might get a little bit more plutonium out of that than you put into it. So you could use a certain amount of plutonium as fuel originally and get a little more out of it at the end of the day. You'd have to reprocess that spent fuel to extract that plutonium so that you could then reuse it as fuel. Now this was they have a great problem with the fuel from that reactor because it's infused with liquid sodium and they can't get it out very easily, and they can't bury it underground because contact with water will make it undergo a violent chemical reaction. So it's a real problem. This fuel is even more difficult to bury than the submarine fuel because of the sodium. Here is the liquid sodium-cooled Fermi 1 reactor outside of Detroit. It melted in 1966. Some of the fuel melted, only a few rods. But that was enough to make it a complete fiasco and a complete shutdown. It was fueled with weapons-grade uranium, not plutonium, but it was intended to breed plutonium through the same method that I was referring to, catching those stray neutrons on a blanket of uranium-238. It's completely shut down, and it's joined the ranks of the cripples in history, the nuclear cripples. Now, the Super Phoenix in France is a large, over 1,000 megawatts breeder reactor, sodium-cooled, widely considered a technological and economic failure due to extreme costs, approximately 9 billion euros, immense political pressure, and poor reliability. It operated for only a fraction of its lifetime, roughly 12 months in 10 years. So that's not a very good performance record, you must admit. So it was a technical fiasco and an economic fiasco, and it was never repeated since. Although that doesn't mean that France has lost interest in breeders. The nuclear countries are generally interested in breeders for the future. Germany built they actually completed building a sodium-cooled reactor, but looking at the experience of France, they decided never to operate it. They simply decided to shut it down even though it was complete, and they turned it into an amusement park. Construction took place from 1973 to 1985. It cost about $4 billion to build, and it never went online at all due to intense public protests and safety concerns. In Japan, the sodium-cooled Monju breeder reactor only operated for less than a year in 3 decades. And now they're scrapping the Monju. The curtain falls on Japan's experimental fast breeder reactor. It's finally pulled the plug, and it's been plagued by accidents, cover-ups, and cost overruns. And that's an article about it. So now in Britain, they had a nuclear reactor that actually ran for a certain period of time, from the 1950s way up to 1994. It was active during that period of time, not always at full power, of course. But the Dunray nuclear breeder is considered a technical success for pioneering what's called fast reactor technology, but it's an environmental and operational failure due to significant radioactive contamination, safety breaches, high decommissioning costs, and it spewed fuel particles onto nearby beaches. These fuel particles are called nuclear fleas, and they're extremely radioactive. It's spent fuel in miniature. They're little particles of spent fuel. Now in New Brunswick, just in the last few years, New Brunswick, the province of New Brunswick, the ARC-100 reactor is a liquid sodium metal-cooled fast reactor with not highly, it's low enriched uranium. It's called HALEU. It means it's much more highly enriched than regular fuel, but not over 20%. Once you get over 20%, you get into the weapons usable domain, and they want to keep it not weapons usable. However, recent articles in Science magazine have pointed out that even this HALEU fuel, which is underneath 20%, could still be used to make nuclear explosives. So it's a problem here of nuclear proliferation again. They wanted to build it. It's in process, but the project is lacking the necessary level of private funding. And we believe it'll never get built. The New Brunswick also has a waste-burning reactor. That's the Moltex reactor. It's a molten salt reactor fueled with plutonium and other actinides extracted from used fuel already stored on site in New Brunswick. That's in limbo. It may not be built either, but it is going right through an environmental assessment at the moment. So who knows? It may be built. That is a possibility. No, excuse me, I mixed up. This one is not going through an environmental assessment. This one is in limbo. The one that's going through an environmental assessment is the one I talked about in the previous slide, the liquid sodium cooled one. In Saskatchewan, they're looking at another small modular reactor called the E. Vinci reactor. It uses uranium at the highest level of enrichment allowed for civilian purposes, 19.76% U-235. We are assured by nuclear scientists, even those who work at Los Alamos in the weapons department, we are assured that that stuff could be used to make atomic bombs. Not efficiently, they would be very heavy. They'd have to be delivered in the hull of a ship or in a container type of thing because they would be big, but they would be very powerful nonetheless. So this is the one that I went back. Excuse me. Now the enrichment of uranium is right now. If you look at this diagram, the red corresponds to the chain reacting type of uranium, which is uranium-235. The gray squares are the uranium which is not chain reacting. And so right now we're using only one square of red, that's about 5% enriched. 5% enriched would be the 6 squares. The 6 squares in the next diagram. That's low enriched uranium. Less than 20%, typically 3 to 5%. Now, highly enriched uranium goes all the way up to 20% uranium-235 and above, and that's a no-no for civilian use. But as I said, when you go to the low-enriched uranium, which is HALEU, that's the second chart there, that is already 85% of the way towards weapons grade. So it's getting very close. It's making it easier if we sell these reactors to other countries, it'll be a lot easier for them to go the rest of the way to weapons grade. You know what's happening in Iran right now with their enrichment, right? Enrichment is a very sensitive technology. Why? Because you can enrich it all the way up to weapons grade, and you can make atomic bombs that are quite low-tech bombs. So reprocessing, which was mentioned earlier about recycling the used fuel, reprocessing is not a good idea for proliferation reasons, because right now there's what I call a firewall, a radioactive firewall between the bomb and the reactor. The reason is that the spent fuel, the irradiated fuel, is so radioactive that when it's freshly out of the reactor, it would kill any human being in 20 seconds at a distance of 1 meter unless they were heavily shielded. Now, it does get less and less radioactive as time goes on, but even after 30 years, it's still very dangerous to handle because of the penetrating radiation that comes off it. So that radioactivity acts as a protection, that you can't just take a fuel bundle out of a reactor and go and make a bomb out of it. You die before you get there. However, if you build a reprocessing plant, what you do is you remove that radioactive barrier and you make the plutonium readily accessible. And it can go out the front door as reactor fuel, but it can also go out the back door for weapons. And that's the danger of reprocessing. And that's why President Jimmy Carter banned plutonium reprocessing in the United States for civilian purposes for that very reason. And he tried to get that ban extended worldwide for the same reason. He was unsuccessful in doing it worldwide, but he was successful in stopping it in the USA. These are tanks of high-level radioactive liquid waste that are left over from reprocessing at Hanford. In Hanford, the cleanup costs, the radioactive contamination is so great that the cleanup costs are estimated by the Government Accounting Office as being somewhere between $300 billion and $640 billion to do a thorough radioactive cleanup of the Hanford site, which of course is a military site. It's where we produce the plutonium for America's nuclear weapons. So let's turn to another advanced concept, which is called using thorium as a fuel. Some people are advocates of thorium, and I hear that even in New York State, thorium has been mentioned as an attractive alternative. I'll be frank with you, thorium does have some advantages. There's no doubt. It's 3 times as abundant as uranium. That's one advantage. And it's also, but it's not really a fuel. Unlike uranium, it's not a fuel. If you put thorium into a nuclear reactor and turn the switch, nothing happens because you have to have something else as fuel. You have to have either uranium-235 or plutonium. That would be either enriched uranium-235 or plutonium. So even before you start a thorium reactor, you have to have access to weapons materials. Plutonium, I should have mentioned earlier, is unlike uranium, all plutonium is usable in nuclear weapons. That's not true with uranium. Natural uranium can't be used in nuclear weapons, and low enriched uranium, 5%, cannot be used either. But plutonium can be used. If you chemically separate it out from the other materials, it can be used to make very powerful atomic bombs at any level. So plutonium is a very special problem. That's why reprocessing is a no-no. Advanced concept of using thorium as a fuel has a similar problem because when a thorium atom, which is not able to undergo a chain reaction, but when it's struck by a neutron, it changes into another material, which is uranium-233. And uranium-233 is an excellent nuclear weapons material. It's an excellent nuclear explosive. And that's the problem with using thorium as a fuel. You create another weapons material, nuclear weapons material. That U-233 can also be used, of course, as fuel for a nuclear reactor. But again, the only way you can get it out of the spent fuel is by using reprocessing. And when you do reprocessing, once again, you make that weapons usable material more accessible to anybody who wants to use it for good or for ill. So now finally, let's just say a few words about nuclear fusion. How's my time?
We're doing okay, but we have to wrap up pretty soon. So,
okay, I only have a few things to say about nuclear fusion. The nature of the beast is, first of all, it's a lot more powerful than nuclear fission. Now, what is nuclear fusion? And in both cases, we're talking about nuclear energy, and it's called nuclear energy because it comes from the nucleus of the atom. As I said before, it's amazing that the smallest thing we can imagine, the nucleus of an atom, contains the strongest force in the universe, the nuclear force. Now, one way of getting nuclear energy is by splitting heavy atoms like uranium or plutonium, and that's nuclear fission. And another way is by combining light atoms into bigger ones. And mostly we talk about hydrogen atoms, and that's why it's called the H bomb. The hydrogen bomb can go up to 15 megatons instead of 15,000 tons. 15 million tons instead of 15,000 tons of TNT, which is the Hiroshima bomb. It could be 1,000 times more powerful than the Hiroshima bomb. But you got to get it going. And remember, I mentioned earlier, the only way you can get that temperature of 100 million degrees to get the fusion reaction going is by using a plutonium ball. A small plutonium bomb gets it up to the fusion area. There are 3 different isotopes of hydrogen, 3 different varieties. They have different masses, but are chemically identical. There's ordinary hydrogen. Then there's heavy hydrogen called deuterium. It's not radioactive. Then there's tritium, which is 3 times heavier than normal hydrogen. And it is the only radioactive isotope of hydrogen. Now, these are the atoms which they use to fuse together in order to create fusion energy. They got to give a lot of heat in order to get those atoms to even come together. The reason why is because they're both positively charged and they repel one another like magnets that push each other away, right? And so you need to have a lot of energy to get them together. And the way they get that energy is to increase the temperature to 100 million degrees. And then you can get them to come into direct contact with each other and fuse into a different element called a helium atom. Now, it's all due to Albert Einstein in 1905 when he was working as a patent clerk because he couldn't get a job as a physicist. He was working as a patent clerk, and in his spare time, he worked out that E is equal to mc squared and published it in a physics journal. E is energy, m is mass, and c is the speed of light squared. That c squared is 90 quadrillion. That's 90 billion million. And if you multiply even a small amount of mass by that number, you get a huge amount of energy. And that's what happens in the Bulletin of Atomic Scientists. They calculate that the amount of mass that was converted to energy in the Hiroshima bombing was about the weight of a butterfly's wing. That's about how much mass was converted into energy. And it's because of that enormous factor, c squared. Well, it turns out that the same thing happens with fusion. When you put these hydrogen atoms together into a larger molecule, a larger atom rather, you lose a tiny bit of mass. It turns out that the end product weighs a little tiny bit less than the constituents that went into it. And that mass that is lost is converted into energy. And that's fusion energy. And it's a lot more than fission energy. So it's a far more energetic reaction. Facts about fusion: temperature has to be over 100 million degrees. Containment has to be non-material, because any material will melt or disintegrate at that temperature. And that's why they use electromagnetic forces, a kind of an electromagnetic bottle. And they call that the tokamak. A tokamak is a donut-shaped electromagnetic bottle that they can keep the fusion fuel in. It's called a plasma. And that plasma is already at a very high temperature. And when the fusion occurs, neutrons are released, which are much more energetic than fission neutrons. We're talking about neutrons that are 14 million electron volts instead of 4 million electron volts. So they're much more energetic neutrons. That means that activation and embrittlement are serious limitations on fusion reactors. Remember I talked about how when neutrons hit non-radioactive materials, it makes them radioactive? It also makes them brittle. And that's what happens here. And activation and embrittlement are going to be serious technical problems. Large amounts of tritium are released to the environment as well. That's an environmental problem. But the big advantage is there's no fission products, no actinides produced, or are there? They could decide to use to make it. They could use a uranium blanket and to produce plutonium from a fusion reactor using those neutrons instead of the fission neutrons. They're not likely to do it in the near future, but you can imagine how they could make weapons-grade fission material using a fusion reaction. So these are the limitations. Now, the big limitation, this is a picture of the Chinese fusion experiment. It's a tokamak type donut-shaped. The biggest problem with fusion is maintaining the fusion reaction for any length of time. So far, the record is about 22 minutes. That's a giant step forward. And that was made in France, the WEST, which is an abbreviation for their tokamak. The previous record was about 17 minutes and 46 seconds, and that was from China at the East tokamak. That's an abbreviation for their tokamak. Before 2024, the record length for fusion was 101 seconds. That's the longest period of time they could get a fusion reaction going. So we're nowhere near to having commercially available fusion. And anybody who tells you that we are is selling you a bill of goods. I have a bridge they could buy. But it is a very exciting field of research, and one can understand how the researchers are enamored of it. But even if they manage to get a sustainable fusion reaction going, that's still a long way from technical feasibility for an actual working reactor. And that's still a long way from economic feasibility. So we're talking about far distant here. We're not talking about something that's going to happen in our lifetime. In fact, we had a tokamak reactor just south of Montreal in a town called Varennes. And I asked the gentleman who ran that tokamak reactor to come and speak to my class. I'm a professor of mathematics and physics at that time at Vanier College. And he said that in his lifetime, he does not expect to see a fusion reaction being a practical reality. And I think that pretty well brings us to the end of our show. I'd just like to mention, however, that people vastly underestimate the potential for renewables. The current electrical capacity in Michigan right now is a bit more than 30,500 megawatts. The potential for offshore wind in Michigan, just Lake Michigan alone, is over 320,000 megawatts. That's more than 10 times the current capacity that is currently installed in Michigan of all kinds, and it's about 1/4 of the total U.S. electrical capacity. So offshore wind in Michigan, there's a link to the study. Um, People really tend to downplay the potential for renewables. They're far more feasible than people believe. The end.
Well, Dr. Gordon Edwards, it's hard to imagine that anybody could listen to your presentation, which was so fascinating, and still have it in their mind that nuclear energy is some sort of solution. I do have a couple of quick questions which we want to get to. We don't have a lot of time left. Um, One of the questions was, can you comment on high burnup fuels dangers?
Now, high burnup fuel is simply to get more power out of the same amount of fuel, the same kilogram of fuel. And you do that by leaving it in the reactor for a longer period of time and enriching the uranium to a higher degree. So that what that really means is that per kilogram, this spent fuel is going to be much more radioactive than the spent fuel we already have. The spent fuel we already have will kill you in 20 seconds. This will probably kill you in 5 seconds. So the problem with the high burnup fuel is that it's much, much hotter. By the way, even when they bury this stuff underground in a deep geological repository, they have to space out the fuel because of the heat generation. It turns out that the heat generated by the radioactive decay of those radioactive atoms, after all, radioactivity is a form of energy. When the atoms disintegrate, they give off energy, and that turns into heat, and it heats up the rocks for about 50,000 years. And Atomic Energy of Canada Limited calculated that the rocks would return to their ambient temperature after about 50,000 years. But in the meantime, you have to space out the waste when you put it underground so that the temperature in between two waste bundles is not over 100 degrees, because you don't want to get steam. Water will be flooding into those cavities eventually. You can't stop it. And you don't want it to boil, because that will create steam, and steam could push the radioactivity out to the environment. So they space out the waste so as to keep the temperature of the rock below boiling point. And that means that even if you reprocess it, even as people mentioned about reducing the waste, that if you reprocess the fuel and take out the plutonium, that maybe you'll then have less waste. Turns out it doesn't make much difference for the geological repository, because the heat is mostly generated by the fission products, and they have to be spaced out. It's the heat from the fission products that causes the melting of the Fukushima reactors and the melting of the Chernobyl reactor. That's really what caused the melting.
Hmm. Another question, by how much would the price of nuclear energy increase in the absence of the Price-Anderson Nuclear Industries Indemnity Act?
I don't think it would be possible to build these plants, because when they first wanted to license nuclear reactors, they had congressional hearings, and they called the heads of all the insurance companies together to Washington to testify. And they said, because they had already produced their own report showing that the property damage would be in the neighborhood of $7 billion at that time. That's in 1957 dollars, by the way. $7 billion in 1957 dollars. And they said, well, can't you insure that? And they said, there's no way we can insure that. And they said, well, come on, why not you? You're insurance companies. They said, no. By law, we have to have the money. We can't just insure something with money we don't have. If we don't have the money, we can't insure it. And we can't cover those losses. So they said, well, why don't you get together with the European Lloyd's of London and all the other European and see if you can make a pool and see if you can do it. And they said, no, it can't be done. As a result, today, if everybody goes home and looks at their homeowner's life insurance policy, you'll find that there's, in the small print of your insurance policy, there's a nuclear exclusion clause, which says your insurance is void in the case of radioactive contamination from a nuclear accident. There's no way that the insurance companies will cover that. That's why the Price-Anderson Act was put there. And also the manufacturers of equipment for nuclear reactors, if they thought that they could be sued, because the Price-Anderson Act gives them a free ride, even if their components were the cause of the meltdown or the cause of the disaster, they cannot be sued. Otherwise, they would not be in the business. They would not make nuclear components if they thought they could be sued.
Mm. Okay, a more technical question. Does spent fuel recycling produce greater volume and more dangerous types of waste, both liquid and gas?
It doesn't create new waste, but what it does is it puts the existing waste into a much more difficult form that to deal with. For example, many of these wastes are gases or vapors, and those are given off. So, for example, a lot of the iodine 129, which is present in great amounts in the spent fuel, iodine 129 has a 17 million year half-life. And in France, where they do reprocess fuel all the time in order to use plutonium to add to the fuel that they already have for their nuclear reactors, they release a lot of that radioactive iodine into the environment. It goes to the thyroid gland and causes damage, especially to children. There were 5,000 children who have to have their thyroid gland surgically removed in Belarus as a result of radioactive iodine coming from the Chernobyl accident. This stuff is given off into the environment and it's not going to go away. This year's emissions are added to last year's, which are added to the years before. It just keeps building up and up and up because 17 million year half-life, we ain't got that much time to wait. The main problem is that you can't get plutonium out of the spent fuel or uranium-233 out of the spent fuel without destroying the fuel bundle. You either have to dissolve it in acid, which releases all the radioactive materials into the liquid solution. That's where those big tanks at Hanford came from, those great big tanks. Those are full of liquid radioactive waste, which is dissolved acid. It's acid-generated dissolved waste from dissolving spent nuclear fuel in order to get the plutonium out for bombs, in most cases originally. Now, there are other techniques for extracting plutonium, but they all involve destroying the solid fuel bundle and releasing all of the contents. It's better to think of the fuel bundles, the fuel assemblies. Don't think of the fuel assemblies as being the radioactive waste. Think of them as being the containers of the waste. The waste is what's inside those fuel bundles. If the fuel bundle is even cracked, it'll release a good deal of radioactivity into the environment. If it's dropped, for example, if it was crushed, then there would be terrific releases. Think of it as the container. If the container is damaged or eliminated, then you have the radioactive contents are free to escape.
Okay. The last question of the day is what do you think we can do to bring past nuclear failings to light and prevent new forms of nuclear power in the future? In other words, where do we go from here and how do we convince our politicians to take the right steps?
It turns out there's a lot of mystification around the subject. People feel disempowered because they feel they're not scientists and therefore they don't feel they can deal with all this scientific business and who to believe as well. Who do we believe? Do we believe this guy? Do we believe that guy? And they haven't got time to take a crash course in nuclear physics. So one of the easiest ways to get at it is through dollars and cents. Just look at the cost of cleanup. Look at the cost of cleanup at Hanford. 300 billion is the low figure, 640 billion is the high figure, according to the Government Accounting Office of a couple of years ago. Similarly, we find by the way, that's because there was reprocessing going on there. If you look at any of the sites in the world where reprocessing was used, they are among the most contaminated sites on Earth in terms of radioactivity. For example, in England, we have a Sellafield in northern England. They did a lot of reprocessing there. And the Irish Sea, as a result, is the most radioactive body of salt water in the world because of discharges into the Irish Sea from that reprocessing plant. Similarly, in Russia, there was a Mayak reprocessing plant on the Techa River, and the Techa River was contaminated. Stalin was so eager to get a nuclear weapon that he could boast about that he urged them to hurry up, hurry up, hurry up. And as a result, they actually dumped liquid high-level waste into the Techa River. And the people downriver from that, this is all a matter of public record, the people downwind from that suffered from a lot of illnesses. That the doctors were forbidden to use the word radioactivity, so they coined a phrase. They called it that the people were getting sick and dying of what they called vegetative syndrome. And vegetative syndrome was simply radiation poisoning, but they didn't want to say so. The worst thing happened in 1957 when one of those liquid tanks exploded and spread radioactive contamination over a very large area. It wiped 30 towns off the map. They had to be totally evacuated for permanently. And it created a radioactive tract of land, which is off limits to humans even today, because that's where the plume, that's where all that radioactive junk in the tank. You have to remember that when you reprocess nuclear fuel, the stuff that's in the tank of leftovers is not just 1 year's worth of nuclear fuel, but many, many years worth of nuclear fuel from many, many reactors. And consequently, it's an enormous inventory. So when that tank blows, it's way, way bigger than any nuclear reactor blowing. So that explosion in 1957 released far more radioactivity than the Chernobyl accident.